Good morning, everyone. Welcome back to Chemistry 101. Today, we're diving into Chapter 2, Molecules and Compounds. This chapter will help you understand the properties of matter, the structure of atoms, and the organization of the periodic table. Let's get started. Unit 1, Molecular Representation. Chemical formulas. Types of chemical formulas. Empirical formula, the simplest ratio of elements in a compound. Example, the empirical formula of hydrogen peroxide, H2O2, is HO. Molecular formula, the actual number of atoms of each element in a molecule. Example, the molecular formula of glucose is C6H2O6. Structural formula, a detailed representation showing how atoms are bonded in a molecule. Example, the structural formula of ethanol is CH3CH2OH. Writing and interpreting chemical formulas. To write a chemical formula, identify the elements involved and the number of each type of atom. For ionic compounds, combine cations and anions in ratios that result in a neutral charge. For covalent compounds, use prefixes to indicate the number of each type of atom. Molecular geometry. VSEPR theory and predicting molecular shapes. VSEPR theory, valence shell electron pair repulsion theory, predicts the shape of molecules based on electron pair repulsion. Linear, bond angle of 180 degrees. Example, CO2. Trigonal planar, bond angle of 120 degrees. Example, BF3. Tetrahedral, bond angle of 109.5 degrees. Example, CH4. Trigonal bipyramidal, bond angles of 90 degrees and 120 degrees. Example, PCl5. Octahedral, bond angle of 90 degrees. Example, SF6. Lewis structures. Drawing Lewis dot structures for molecules. Count the total number of valence electrons. Write the skeleton structure with single bonds. Distribute remaining electrons to satisfy the octet rule or duet for hydrogen. Place any extra electrons on the central atom. Resonance structures and formal charge. Resonance structures, different possible structures for a molecule that cannot be represented by a single Lewis structure. Formal charge, helps determine the most stable resonance structure. Models of molecules. Ball and stick, space filling, and skeletal models. Ball and stick model represents atoms as balls and bonds as sticks, showing the structure clearly. Space-filling model, atoms are shown as overlapping spheres, representing how the molecule occupies space. Skeletal model, simplified model showing bonds between atoms as lines, often used for organic molecules. Visualizing molecules in 3D. Use models in software to visualize molecules in 3 dimensions to understand their shape and reactivity. Unit 2, Nomenclature, naming compounds. Ionic compounds. Naming binary ionic compounds. Name the cation, metal, first, then the anion, nonmetal, with an -ide suffix. Example, NaCl is sodium chloride. Naming ionic compounds with polyatomic ions. Name the cation first, followed by the polyatomic ion. Example, NaNO3 is sodium nitrate. Covalent compounds. Naming binary covalent compounds. Use prefixes to indicate the number of each type of atom. The second element ends with -ide. Example, CO2 is carbon dioxide. Prefixes for indicating the number of atoms. 1. Mono. 2. D. 3. Tri. 4. Tetra. 5. Penta. 6. Hexa. 7. Hepta. 8. Octa. 9. Nona. 10. Deca. Acids and bases. Naming acids. Binary acids, hydro prefix, followed by the root of the nonmetal and icy suffix, plus the word acid. Example, HCl(Aq) is hydrochloric acid. Oxyacids, no hydro prefix. If the polyatomic ion ends in ate, change to IC. If it ends in ite, change to us, followed by acid. Example, H2SO4 is sulfuric acid, from sulfate, H2SO3 is sulfurous acid, from sulfite. Naming bases. Name the cation followed by hydroxide. Example, NaOH is sodium hydroxide. Special naming rules. Common names versus systematic names. Common names are traditional and often used in everyday language, e.g., water for H2O. Systematic names follow IUPAC rules for clarity and consistency. Naming organic compounds, basic introduction. Organic compounds are named based on the number of carbon atoms and the type of bonds present, alkanes, alkenes, alkynes. Example, methane, CH4, ethene, C2H4, ethene, C2H2. Real-world considerations and modern-day applications. Chemical formulas. Medications. Understanding chemical formulas helps in designing drugs with specific molecular compositions. Materials science. Engineers use chemical formulas to develop new materials with desired properties. Molecular geometry. Pharmaceuticals. The shape of drug molecules affects their interaction with biological targets. Agriculture. Pesticides are designed with specific molecular geometries to target pests effectively. Lewis structures. Environmental chemistry. Predicting the behavior of pollutants and designing molecules for environmental cleanup. Nanotechnology. Designing molecular structures for advanced materials and devices. Models of molecules. Education. Molecular models help students and scientists visualize and understand complex structures. Research. 3D visualization of molecules aids in the development of new chemical reactions and materials. Nomenclature. Healthcare. Proper naming of compounds ensures clear communication in medical prescriptions and treatments. Chemical industry. Standardized naming conventions facilitate global trade and regulatory compliance. Conclusion. Today, we covered the essential topics in molecular representation and nomenclature. Understanding chemical formulas, molecular geometry, Lewis structures, models of molecules, and the systematic naming of compounds is crucial for mastering chemistry. These concepts are fundamental for scientific study and practical applications in various fields. Thank you for joining today's lesson, and stay tuned for our next chapter. Thank you for joining today's lesson on Chapter 2, Molecules and Compounds. Stay tuned for our next chapter, where we will explore molecules and compounds. Don't forget to like, subscribe, and share this video. Until next time. Dr. Siegfried Howell.